All right, let's talk about the world around us. Have you ever stopped to think about the hidden math, the geometry that's literally everywhere? I mean, from the soda can on your desk to the planet we're standing on, it's all governed by these really cool geometric ideas. So let's dive in and see how it all works.
No, seriously, think about it for a second. Are these just silly, random questions, or can we actually figure this stuff out? Well, the answer is a huge yes. And you know what? The tools we need are way simpler and more beautiful than you probably imagine. We're not talking about some abstract homework problem here. This is real-world stuff.
And you know what? We're going to use this very problem right here as our guide today. We've got a fountain pen, we've got a bottle of ink, and we have one big question. How many words can you actually write with that? I promise you, by the time we're done here, you're going to know the answer. But even better, you're going to understand exactly how we figured it out. Okay, so to get started on this journey, we've got to meet the main characters of our story. Think of these as the three 3D superstars, the basic building blocks for just about everything. First up, we have the cylinder. What makes a cylinder a cylinder? It's that perfectly round shape that's the same all the way up. It's totally straight. And that's why it's so useful for things like cans of soup, pipes, batteries, anything you need to stack or roll or just hold stuff in a really predictable way. Next up, the cone. Pretty simple, right? It's got a flat circular bottom, and then it goes all the way up to a single point. It's that classic pointy shape you see everywhere, from traffic cones and party hats to, of course, the best use of all, holding a big scoop of ice cream. And last but not least, the sphere. Honestly, in a lot of ways, this is the most perfect shape there is. Think about it. Every single point on its surface is exactly the same distance from the center. It's just perfect. And that beautiful symmetry is probably why we see it all over in nature, from a tiny raindrop to a giant planet. Okay, so we've met our three shapes. Now, to really understand them, there are basically two big questions we can ask. And these two ideas, well, they're the key to unlocking pretty much all of their secrets. And here they are, volume and surface area. It's actually pretty simple. Volume is just how much stuff can you fit inside it. If you were to fill it up with water or sand, how much would it hold? Surface area, on the other hand, is all about the outside. If you wanted to wrap it like a present, how much wrapping paper would you need to cover its entire skin? That's it. Inside versus outside. All right, let's peek at the recipes for our cylinder. To find its volume, it's just pi times the radius squared times the height. That r is just the radius of that circle on the bottom, and h is how tall it is. A good way to think about it is you're just taking the area of that circle and stacking it up h times. Now, the surface area formula is a little trickier, but only because you have to remember to add the two circles, the top and the bottom, plus that whole curved part on the side.
Now check this out. When we look at the cone, there's something really cool about its volume formula. It is exactly 1/3 the volume of a cylinder that has the same base and the same height. Isn't that wild? It's such a neat, clean relationship. Okay, and for its surface area, you'll see a new letter in there, L. That's just what we call the slant height. It's not the straight up and down height, but the length measured down the side of the cone, from the pointy tip to the edge.
And finally, the sphere. I just love how simple and elegant this is. Look at those formulas. Everything, both the volume and the surface area, depends on just one thing, the radius, r. That's it. No height, no slant height, nothing else to worry about. You just need that one single number, the distance from the center to the edge, and you know everything about it. So cool. Okay, we've got the formulas, we've got the tools. Now for the really fun part. Let's actually use them. What happens when we take something solid and we completely change its shape? So picture this. You've got three little iron spheres. You toss them into a furnace, melt them all down into one big puddle of liquid iron, and then you pour that into a new mold to make one single giant sphere. Here's the question. Did you lose any iron? The shape is totally different, for sure, but is the amount of stuff the same?
The answer is nope, not a single drop. And this is a super important idea. When you melt something down and reshape it, the volume stays exactly the same. You didn't create any new iron and you didn't destroy any, you just rearranged it. So that means the volume of those three little spheres added together has to be exactly the same as the volume of the one big sphere you made. It's a perfect trade.
Okay, so we know we can track stuff even when it changes shape. But what about things that are already complicated to begin with? I mean, the real world isn't just full of perfect spheres and cylinders, right? Or is it?
Let's try a challenge. Say you have a cylinder filled with water.
and you drop a solid metal cube into it. Obviously, the water level is going to rise, but by exactly how much? This isn't something you have to guess. You can calculate it. So how do these two different shapes, the cube and the cylinder, talk to each other in this problem?
And here's the aha moment. It's so simple and so brilliant. That cube has to push water out of the way to make space for itself, right? Well, the amount of water it pushes up, the displaced water, has to have the exact same volume as the cube itself. So the volume of that little slice of water that rose up is equal to the volume of the cube. That's the whole secret right there.
Okay, on to the next challenge. Now look at this little toy. This is, well, it's not just a cone, and it's not just a sphere. It looks like a cone stuck on top of half a sphere, a hemisphere. So how in the world are we supposed to figure out the volume of that thing?
Turns out, it's way easier than it looks. You just treat it like geometric Legos. You break it down. You calculate the volume of the cone part on top. Then you calculate the volume of the hemisphere part on the bottom. And then, you just add them together. That's it. You just deal with each simple shape one at a time.
So where does all this leave us? I mean, what's the big takeaway? It's not just about memorizing a few formulas. It's about getting a new way to see the world. It's like you've been given mathematical X-ray vision to see the hidden structure in everything.
And that brings us all the way back to where we started. That fountain pen, remember? Well, now we can look at that ink barrel and just see it for what it is, a simple cylinder. We can calculate its volume. And once we know that, and we know roughly how many words you get from a tiny drop of ink, we can figure out the whole thing. And the answer is a whopping 45,100 words from just one little barrel of ink. That right there is the power of geometry.
So, let's do a quick recap of your new superpowers. First, you get volume. That's the how much fits inside question. Second, you get surface area. That's the how much material to cover it question. And third, you get conservation. The idea that stuff doesn't just vanish when you change its shape. These three things are the keys to the kingdom.
And that's where I'm going to leave you. I want you to look around right now. Look at the coffee mug next to you, the basketball in the garage, the can of beans in the kitchen. They're not just things anymore, are they? They're puzzles. They're collections of cylinders, spheres, and cones, just waiting for you to figure out their secrets. So, the only question left is, what are you going to measure first?